Let's talk about the constitutive relation for Casson fluid and also blood. Casson fluid is a type of non-Newtonian fluid. Casson fluid, non-Newtonian. And usually it will, if you look at the tau versus gamma curve, it will look like this way. And then you have something like tau y. Tau y is called the yield stress. So this is the minimum stress you need to apply to the fluid in order to let it flow. If the stress on the fluid is less than this yield stress, then it will not flow. It will behave like a solid. So if tau shear stress is less than tau 1, then no flow, like a solid. Maybe let's let's just put this in this way so far. Later on, we will be more specific about the sign and being positive and negative. Right now you can, or we can just look at this. Or maybe let's start here. Okay, let's put an absolute sign. And if the shear stress is greater than the yield stress, then you would expect fluid motion. The reason I put absolute sign on that is because shear stress and the shear rate, as we have been discussed in the past, if you follow a regular mechanics notation and the derivation, they can be either positive or negative. Those are signed physical quantities. And when we talk about the constitutive relation for a Casson fluid, when you see a curve like this, it's not derived from first principle. It's rather an empirical relation. So it's an empirical model. Means it can be like fitted from experimental data or from other empirical experience. So it's not from first principle. So that's why when people, for example, when people measure something, doing experiment, what they usually get or care about is the magnitude of the shear stress and the magnitude of the shear rate. And then when you look at the curve like this, and they meant to say the magnitude, but it doesn't mean shear stress and shear rate are always negative. They are always positive. They can be negative. What the empirical model says is only the magnitude of it. So for this reason, we will put the absolute sign to it just to recognize that regularly speaking, they are signed values. But when we compare with the yield stress, we are comparing the magnitude or in the absolute sense. So blood is a type of Casson fluid. Blood is a type of Casson. And we discussed it a little bit in the past because of the red blood cells. So due to red blood cells, those red blood cells want to aggregate. And if you have low shear stress applied to the aggregated red blood cells, the cells are just aggregated together, behave as a solid. And only when you break the stress like limit, we use high enough shear stress to push the blood, and those red blood cells, they will not aggregate, they start to flow. And that's why the discussion of Casson fluid is specifically relevant when we talk about the biotransport phenomenon. So let's look at the blood. We know that blood is non-Newtonian fluid. So when you describe a blood, you cannot use a single viscosity to say this is the viscosity of the blood. You need to say at which flow rate you will expect which level of viscosity. So that means you need to talk about apparent viscosity instead of its unique viscosity. So you need to talk about apparent. Apparent viscosity is a function of gamma dot. Let me draw like a diagram to show how the apparent viscosity of blood may look like. So this is in the unit of centipoise. I draw in log scale 110 and 1. And here is shear rate, gamma dot, is in the unit of 1/2. So let's see, there is 0.1, there is 1, there is 10, there is 100, it's 1,000. Okay. So when the shear rate is low, like around 0.1, the apparent viscosity is pretty high, and then it drops with the increase of the shear rate. So if you draw a curve, it decreases and eventually it plateaus. So the plateau, the value, this is about 3. So when we talk about blood, usually we would say whether we are at a low shear rate region or at a high shear rate region. So if you are saying, well, this is for blood, and then we put it in blood. So at a low shear rates, when we say low shear rates, it's usually below 100 per second to 200 per second. At low shear rates, we have pretty high viscosity, so we have elevated blood viscosity. At high shear rates, usually it is up to 1,000 or at a very high, so usually we are seeing gamma dot to be large. Then the apparent viscosity stabilizes at a asymptotic value. So it's approximately 3 to 4 centipoise. So usually we use mu infinite. Infinite means the gamma dot is infinite. So at infinitely large shear rate, it's approximately 3 centipoise. 3 centipoise is same as 0.003 Pascal second. So this is the apparent viscosity of blood. And now let's look at the constitutive relation. Let me draw again, this is tau versus gamma dot. This curve, tau y. So this curve, people have fitted it in the past. So scientists figured out that you can describe this curve by this equation. The magnitude of tau, square root of the magnitude of the shear stress equals to the magnitude of the yield stress squared, not squared, square root of the magnitude of the yield stress plus S multiplied by the square root of the magnitude of the shear rate. So S is a constant related to the viscosity. And the tau y and the S are material specific. So different materials would have different constant tau y and S. So when I say a constant, it means it's not a function of gamma dot. However, tau and S, they are affected by other things. For example, they are affected by temperature or constitution or other things. So it's important to know that these material specific and affected by temperature, control, CH, etc. So when you study Casson fluid, if you want to measure like the constitutive relation or stress-strain relation, you need to specify at which conditions you obtain these. But once you fix that condition, then the tau y and S are constant. They are independent of the shear rate, the gamma dot. Okay, so when we talk about for the blood, like at high shear rate, we said that the mu infinite is about 3 centipoise. This is at body temperature 37 degrees C. Let's look at how to interpret the parameter S. We discussed what is tau y. This is the minimum shear stress you need to apply to the Casson fluid in order to break it, in order to let the flow. So let's look at S. To interpret S, let's look at the higher shear rate limit. It's a high shear rate limit. That means when tau is much larger than tau y. And that means it's much larger than like the minimum shear you need. So in this case, and you would see that tau or square root of tau is approximately equal to S multiplied by the square root of gamma dot. So if you compare this equation with the original constitutive relation, so we dropped the tau y term. This is because if you have two terms like the tau y term plus S multiplied by the gamma dot term, if the gamma dot term dominates much larger than the tau y term, then you can neglect a small term. It's as if you add like 0.01 to like 1,000. You will approximately get 1,000, something like that. So you can neglect the small terms. And for this reason, at a high shear rate limit, the shear stress, square root of the shear stress is approximately equal to S multiplied by the square root of the shear rate. And then you can square both sides. What you get is tau being approximately equal to S squared gamma dot. Now, if you look at this equation, this is very close to a Newtonian relation. It's almost approximately Newtonian relation because for Newtonian fluid, you have tau being equal to a constant multiplied by the shear rate. Now S squared serve as this constant. So this is at a high shear rate, it's approximately Newtonian. And we just discussed that at a high shear rate, the effective viscosity is about 3 centipoise. So now we can say S squared is approximately 3 centipoise. So you can get S is approximately square root of mu infinite equal to square root of 3 centipoise is about 1.732 centipoise to the power of 1/2. It's a weird power or dimension that is viscosity, square root of viscosity. And these type of weirder dimensions, it doesn't come naturally. So if you derive things from first principle, you won't get something like this. So it's also clear that it's a fit. It's as an empirical relation. Only when we fit things and some weird things can come out. Because you try to fit a line, you are not following any like physical laws or anything. You just observe the experimental data and then you try to say what it is. And then when you fit and if you work on those fields a lot, or if you get enough experience, you know that when you fit the data, you will get a lot of parameters. And then those parameters sometimes can have non-typical dimensions. So this S is such an example. So if you want to interpret this empirical relation, what is S? S is the square root of viscosity at a high shear rate limit. Okay, so this is the constitutive relation for Casson fluid, and this is also the constitutive relation for blood. Let's look at an example. Estimate pressure drop required to overcome the yield stress is small cylindrical blood vessel. So the yield stress is usually 4 times 10 to the power of 3 Pascal. So it's a very small number. So it's not so hard to break the red blood cells. You don't need too much effort. Well, that must be true. Otherwise, if we need a lot of stress to break the aggregates of red blood cells, then our body must be under a high stress. Our blood vessel need to constantly have very high pressure to push through. That may not be ideal. So we don't need too much pressure. And assume for this problem, assume L divided by R. So the length of the blood vessel divided by the radius of the blood vessel is 200. Okay, let's see how do we analyze this problem. So here is our blood vessel. And then we know that from our analysis of force balance, we know that tau RZ is R divided by 2 dp dz, or is equal to minus R delta P 2L. So it's linear in R. So at the center line, where R equals 0, there's no tau RZ, but it linearly increases along the radial direction. So this is our profile. Actually drawing along the opposite directions. Let me join this direction. So that we recognize that it's a negative shear stress. This is tau RZ as a function of R. So this is our R coordinate. This is our Z coordinate. So you can see that at the center line of the blood vessel, the theoretical shear stress is 0. So 0 is always less than the yield stress. So you know on the center line that there won't be any fluid motion. It's behave like a solid. But in order to let the blood to overcome yield stress, in order to let the blood to flow in the blood vessel, at least we want the wall shear stress being larger than the yield stress. So what we want is tau W on the wall, at least this should be larger than tau 1. Otherwise, if the maximum shear stress in the blood vessel, tau W is less than tau 1, then there would be no flow motion at all through the entire blood vessel. So that would be too bad. So the question asks us how to find the pressure drop delta P so that at least we have this condition being satisfied. Okay, so now tau W, what is tau W? Tau W is tau RZ evaluated at R equal to capital R's wall shear stress. So it would be R delta P divided by 2L. And then we want these to be larger than tau 1. So now we can see our delta P must be larger than 2L tau 1 divided by R. Let's put it in numbers. We have 2 multiplied by 200. This is the ratio of L divided by R, multiplied by the yield stress, 4 times 10 to the negative 30 Pascal. Okay, let's multiply this together. You get 1.6 Pascal. So just give you a perspective how large it is. The pressure in the blood vessel is on the order of 10 to the power of 4 Pascal. So typical pressure just putting aside the noise. Typical mean arterial pressure is about 10 to the power of 4 pascal. So indeed, the pressure requirement, the pressure drop across a vessel in order to generate blood flow is indeed very small compared to the pressure itself of the blood. Okay, that's all I would like to talk for today's lecture. Before we close, let me leave an exercise for you guys. The homework. Explain why blood exhibits shear staining behavior and how this is captured by the Casson model. What happens to the what happens to the apparent viscosity as the shear rate increases. This is sort of a conceptual review of what we discussed in this lecture.